Hello my friend, welcome back to the Sleepy Professor channel. I'm glad to see you again. Tonight we're going to embark on a gentle journey together, one that takes us far beyond the boundaries of our daily lives, up into the quiet expanse of the night sky where something truly magical happens. We're going to explore the northern lights, those mystical curtains of colour that dance across the polar heavens. But we're not just going to learn about them, we're going to let them guide us into a place of deep rest and wonder. So settle into your most comfortable position. Let your breathing slow and deepen, and allow my voice to carry you through this cosmic story. Let's begin our journey at the very heart of our solar system, 93 million miles away from where you're resting right now. The sun, that ancient glowing furnace that warms our days, is far more than just a source of light and heat. It's constantly breathing in its own way, exhaling a gentle stream of particles into the vast emptiness of space. This breath, known as the solar wind, isn't really wind as we know it. There's no air rushing past, no leaves rustling in its wake. Instead, it's a continuous flow of charged particles, mostly electrons and protons, streaming outward from the sun's corona at speeds that would make your head spin if you thought about them too quickly. But tonight, we're not thinking about speed or urgency. We're thinking about the gentle, patient journey these particles make, drifting through the cosmic dark like seeds on a breeze, each one carrying a tiny spark of the sun's infinite energy. These particles don't travel with any particular destination in mind. They simply move outward in all directions, spreading through space like ripples on an infinite pond. Most of them will journey forever into the void between stars, but some, just a fortunate few, will encounter our Earth after travelling for about 2 or 3 days through the emptiness. It's a slow, dreamy voyage when you think about it in cosmic terms, these tiny pieces of the sun drifting silently through space, passing by Mercury, passing by Venus, until finally they approach our blue-green home, still moving, still carrying that solar energy with them. Now, as these particles approach Earth, something wonderful begins to happen. Our planet, you see, isn't defenseless against the constant bombardment from space. Deep within Earth's core, there's molten iron constantly churning, rotating with the planet's spin. And this movement creates something invisible yet immensely powerful, a magnetic field that extends far out into space, wrapping our entire world in a protective embrace. Scientists call this region the magnetosphere, and it stretches out tens of thousands of miles beyond our atmosphere, like an enormous invisible shield. When the solar wind encounters this magnetic field, the charged particles don't simply crash into Earth. Instead, they're gently redirected by the magnetic forces flowing around our planet like water around a smooth stone in a stream. The magnetosphere compresses on the side facing the sun, pushed inward by the solar wind's pressure, while on the night side it stretches out into a long tail, creating what scientists call the magnetotail. It's a dynamic, flowing boundary, constantly shifting and adjusting as the strength of the solar wind ebbs and flows, as the sun's breath grows stronger or softer, with its own rhythms and cycles. But here's where the magic truly begins, my friend. While most of the solar particles are deflected around Earth, some of them find a way in. You see, Earth's magnetic field lines aren't a perfect sphere. They emerge from the magnetic South Pole, arc high above the planet, and converge again at the magnetic North Pole. Near these polar regions, the magnetic field lines actually funnel down toward Earth's surface, like invisible pathways leading into our atmosphere. The charged particles from the solar wind follow these field lines spiraling down along them, drawn inexorably toward the poles like dancers being guided by an invisible choreographer. This process isn't violent or sudden. It's a gentle, continuous flow, like water trickling down a mountainside following the path of least resistance. The particles spiral along the magnetic field lines, moving faster as they descend, their energy building as they approach Earth's atmosphere. They're still invisible at this point, still silent, carrying their solar energy through the vacuum of space. And all of this is happening right now, as you rest here, as your breathing deepens and slows. The solar wind is flowing, the magnetic field is guiding, and the stage is being set for the aurora's appearance. The journey these particles take is measured not just in distance but in layers. As they descend along the magnetic field lines, they pass through different regions of near-Earth space. First comes the outer magnetosphere, where Earth's influence begins. Then they move through the plasma sheet, a region where magnetic energy is stored and sometimes released in brilliant bursts. Deeper still, they approach the upper reaches of our atmosphere, that thin envelope of gases that makes life possible on our planet's surface. And it's here, in this transition zone between space and sky, where the aurora is born. Think about the patience required for all of this to happen. The sun releases its breath continuously, every moment of every day for billions of years. The particles travel for days through space. The magnetic field stands as an eternal guardian, never resting, never faltering, and we, tiny beings on a small planet, get to witness the result of all these cosmic forces working together, the Northern Lights. There's something deeply calming about being part of such an ancient, ongoing process, don't you think? It puts our own worries into perspective, reminds us that we're part of something much larger and more beautiful than our daily concerns. The solar wind itself varies in strength and density. Sometimes it's a gentle breeze, carrying only a thin stream of particles. Other times, when the sun experiences what scientists call a coronal mass ejection, a massive burst of solar material released from the sun's surface, the solar wind becomes a rushing river of charged particles, carrying billions of tons of solar plasma toward Earth. When these stronger bursts arrive at our planet, they create the most spectacular auroras, filling the sky with brilliant curtains of light that can even be seen at lower latitudes than usual. But even during quiet times, the process continues, the particles flow, and the aurora dances on, perhaps more subtly, but always present above the polar regions. There's a rhythm to all of this that mirrors the rhythms of sleep and rest we seek in our own lives. The sun has its own cycles, growing more and less active over an 11-year period. During solar maximum, when the sun is most active, auroras are more frequent and more intense. During solar minimum, they're quieter, more subdued, but they never stop entirely. Just as your breath continues as you sleep, gentle and regular, the sun continues its breathing, and Earth's magnetic field continues its protective embrace, and the aurora continues its eternal dance. You're drifting now, aren't you? Feeling yourself becoming part of this cosmic rhythm, this gentle flow of energy and light. The temperature of the solar wind, if you can imagine such a thing, is actually incredibly hot, over 1 million degrees Celsius. Yet in the vacuum of space, temperature doesn't mean quite what it does here on Earth. There's nothing to transfer that heat to, no molecules to collide and warm up, so these particles travel through space at incredible temperatures, yet in profound cold. A paradox that reminds us how different the cosmos is from our everyday experience. It's a realm of extremes existing, in perfect balance, much like how in sleep our bodies and minds find their own balance between activity and rest, between thought and emptiness. When scientists first began studying the solar wind in the 1950s and 1960s, they used spacecraft to directly measure this stream of particles. Before that, it was only a theory, proposed by scientists like Christian Birkeland and later refined by others, including Eugene Parker, who correctly predicted many of the solar wind's properties before we could even measure them. Now we have satellites stationed between Earth and the Sun, constantly monitoring the solar wind, giving us advance warning when a particularly strong burst is heading our way. These Sentinel spacecraft, with names like SOHO and ACE, maintain their lonely vigil in space, watching the sun's breath for us, measuring its speed and density, its magnetic properties, all so we can better understand and predict when the aurora will put on its most spectacular shows. Imagine being one of those particles right now, leaving the sun's surface in a dramatic eruption of energy, then spending days coasting through the silent void, Earth growing slowly larger ahead of you as you drift closer. You'd pass the orbit of Mercury, then Venus, tiny worlds compared to your origin and destination. You'd travel through regions of space where the sun's light takes minutes to reach, where the concept of up and down has no meaning, where you're surrounded by infinity in all directions. And then, finally, you'd feel the first gentle tug of Earth's magnetic field, beginning to redirect your path, to guide you not toward the planet's equator, where most of the landmass and population resides, but toward the poles, toward the cold, dark regions where winter nights can last for months, and the aurora is not just a rare visitor, but a constant companion to those who live there. The magnetosphere itself is a wonder worth contemplating as you settle deeper into rest. It's not static, but constantly moving, responding to changes in the solar wind like a sail responding to shifts in the breeze. When the solar wind is calm, the magnetosphere expands, reaching farther out into space. When a strong burst hits, the magnetosphere is compressed, pushed back toward Earth, and this compression stores energy in the magnetic field lines, energy that will later be released in the form of enhanced auroral displays. It's a system in constant flux, yet always maintaining its essential structure, always protecting Earth from the full force of the sun's radiation. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, much as it did on Mars billions of years ago when that planet lost its own magnetic field. So the aurora, in a way, is not just beautiful but a visible sign of the invisible protection that makes life on Earth possible. The journey of the solar particles is one of transformation. They begin as part of the sun, born in the nuclear furnace, of its core where hydrogen atoms fuse into helium, releasing energy that eventually makes its way to the sun's surface and beyond. They're ejected into space as part of the solar wind, carrying with them a tiny fraction of the sun's energy. They travel through the void, transformed from part of a star to wanderers in space. They encounter Earth's magnetic field and are transformed again, redirected, channeled, guided toward the poles. And finally, when they collide with molecules in Earth's atmosphere, they transform one last time, their kinetic energy converted into light, into the shimmering, dancing curtains of the aurora. It's a complete cycle of energy and transformation, beginning 93 million miles away and ending in a moment of beauty that takes your breath away if you're lucky enough to witness it. Now, my friend, as you rest here in comfort, let's gently shift our attention to what happens when those solar particles, having completed their long journey, finally reach Earth's atmosphere. This is where the invisible becomes visible, where energy transforms into light, where the aurora truly comes to life in all its colourful glory. The atmosphere you're breathing right now, the same air that fills your lungs with each slow, deep breath you take, is made up of different gases, each with its own properties, its own personality, if you will. The two most abundant gases are nitrogen and oxygen, and these are the stars of our aurora story, the ones that paint the night sky with colour. When a charged particle from the solar wind collides with a molecule of gas in the upper atmosphere, something beautiful happens at the atomic level. The collision transfers energy to the atmospheric molecule, exciting its electrons, bumping them up to higher energy states. But electrons don't like to stay in these excited states. They want to return to their normal ground state, and when they do, they release the extra energy as light. It's a bit like pressing down on a piano key and then releasing it. The key wants to return to its resting position, and in doing so, it creates a sound. With atoms and molecules, the return to the ground state creates light instead of sound, and the colour of that light depends on which gas is involved and how much energy was transferred in the collision. Oxygen is the primary artist when it comes to the aurora's most common colour, that ethereal, luminous green that most people picture when they think of the northern lights. When oxygen molecules at an altitude of around 100 to 150 kilometers above Earth's surface are struck by solar particles, they emit a beautiful greenish-yellow light. This is the aurora at its most typical, most recognizable form. It's the color that dominates photographs and memories, the shade that seems almost otherworldly in its purity and brightness. If you've ever seen the northern lights, chances are this is the color you remember most vividly: green, glowing, alive with movement as it dances across the sky like curtains blown by an invisible wind. But oxygen has another trick up its sleeve, so to speak. At higher altitudes, above 200 kilometers, where the air is even thinner and the collisions happen less frequently, oxygen produces a deep, rich red light. This red aurora is rarer, more elusive, requiring very strong solar activity to appear. It's the aurora of legends, the one that ancient peoples sometimes interpreted as blood in the sky, as omens of war or disaster. But there's nothing ominous about it when you understand the peaceful process behind it. Simply oxygen molecules, far above the green aurora layer, slowly releasing their energy as crimson light, taking more than a minute sometimes to emit a single photon. The red aurora is patience personified, a gentle reminder that some of the most beautiful things in life take time to reveal themselves. Nitrogen, the other major component of our atmosphere, contributes its own colours to the aurora palette. When nitrogen molecules are struck by highly energetic particles, they can emit blue or purplish-red light, depending on whether the nitrogen molecule loses an electron in the collision or not. The blue light tends to appear at the lower edges of aurora displays, adding depth and contrast to the green curtains above. The purplish-red, meanwhile, can blend with oxygen's reds to create stunning magenta hues that seem almost too vivid to be real, like someone has painted the sky with watercolors directly from their imagination. What's particularly soothing to contemplate is that all of these colors are happening simultaneously, layered on top of each other like a cosmic parfait. The lowest reaches of the aurora, down around 80 to 100 kilometers, might show blue from nitrogen. Above that, from 100 to 250 kilometers, you'll see the dominant greens and yellows for oxygen. And higher still, the rare reds emerge, visible only during the most intense displays. Each layer is distinct, yet they blend seamlessly when viewed from the ground, creating curtains and arcs and corona effects that shift between colours as the aurora moves and evolves. It's like watching a painter work on a canvas the size of the sky, adding layers of colour, blending them, letting them flow into each other in ways that seem both random and perfectly intentional. The intensity of the colours also varies with the energy of the incoming particles. Gentle solar wind produces gentle, subdued colours, pale greens, soft pinks, colours that are almost dreamlike in their subtlety. Stronger solar storms produce brighter, more saturated colours, electric greens that seem to glow from within, deep reds that stretch across the entire sky, blues and purples that accent the display like highlights in a master painting. There's a direct connection between the violence happening on the sun's surface and the beauty appearing in our sky, but somehow that violence is transformed into something peaceful and serene by the time it reaches us, filtered through space and time and the gentle processes of atmospheric physics. If you could somehow float up into the aurora, and let's imagine you could, safely and comfortably just drifting upward like a balloon rising into the sky, you'd notice something interesting. From the ground, the aurora appears to be a solid curtain or arc of light, but as you rose up into it, you'd discover that it's actually made up of countless individual rays, vertical structures aligned along Earth's magnetic field lines. Each ray is like a single stroke of a brush, and together they create the larger pattern we see from below. These rays can be hundreds of kilometers long, but only a few hundred meters wide, and they flicker and pulse with changes in the solar wind, sometimes appearing and disappearing in the span of a few seconds, sometimes persisting for minutes or even hours. It's a level of structure and detail that's hidden from casual observation but reveals itself to those who look closely, who take the time to truly see what they're witnessing. The green aurora, that most common colour, has a wavelength of 557.7 nanometers, a very specific frequency of light that corresponds to the energy released when an excited oxygen atom returns to its ground state. Scientists can measure this wavelength precisely using instruments called spectrometers, confirming that what we're seeing is indeed oxygen emission and not some other phenomenon. There's something oddly comforting about this precision, isn't there? The universe operates according to laws we can measure and understand, yet the result is still magical, still capable of inspiring wonder even when we know exactly what's happening at the molecular level. Understanding doesn't diminish beauty. If anything, it enhances it, adding layers of appreciation to the visual spectacle. Occasionally, under specific conditions, the aurora can appear to be white or yellow-white to the naked eye. This happens when multiple colours are being emitted at once, and our eyes, which are not as sensitive to colour in low-light conditions, blend them together into a paler, less saturated hue. Photographers with their long exposure cameras often capture colours that observers on the ground can barely see, because the camera sensor is more sensitive and can accumulate light over time, bringing out the greens and reds and purples that the human eye perceives as pale grey or white. This is why photographs of the aurora often look more vibrant than eyewitness descriptions. The camera is seeing something closer to what's actually there, while our eyes, marvellous as they are, have limitations in the dark. The altitude at which auroral colours appear is determined by the density of the atmosphere at different heights. Down low, where the air is thicker, collisions between particles and atmospheric molecules happen more frequently. This means the excited atoms and molecules release their energy quickly before they have time to drift apart or be disrupted. Higher up, Where the air is thinner, collisions are rarer, and excited atoms might hold on to their energy for a longer time before finally releasing it as light. This is why the red oxygen emissions appear at high altitudes. The oxygen atoms are able to stay in their excited state longer in the thinner air, eventually releasing that characteristic red photon. It's a gentle process, unhurried, taking place over timescales that seem almost meditative when you think about them. An atom absorbing energy, holding it, and then finally peacefully releasing it as a single particle of red light. There's also something called proton aurora, which is different from the more common electron aurora we've been discussing. Proton aurora occurs when hydrogen ions from the solar wind capture an electron from atmospheric molecules, becoming neutral hydrogen atoms in the process. These newly formed hydrogen atoms then emit light, creating a more diffuse, less structured glow compared to the curtain-like electron aurora. Proton aurora is usually too faint to see with the naked eye, but it's there nonetheless, adding its subtle contribution to the overall light show, a quiet background performer supporting the main attraction. The specific colours of the aurora have varied meanings in different cultures throughout history. Some indigenous peoples of the Arctic saw the green lights as spirits of their ancestors dancing in the sky. Others saw them as reflections from distant fires, or as harbours where souls of the unborn waited to descend to Earth. The red aurora, being rarer and more dramatic, often carried darker interpretations, warnings of war, harbingers of disaster. But from our modern perspective, with our understanding of atmospheric physics and solar-terrestrial interactions, we can appreciate the colours simply as what they are: natural consequences of energy transfer, beautiful byproducts of the sun's influence on our planet, neither good nor evil, neither lucky nor unlucky, just endlessly, timelessly beautiful. As you lie here, breathing slowly, perhaps you can imagine these colours in your mind's eye. Picture that luminous green first, spreading across the northern horizon like a fog made of light. Then add touches of red at the top, fading into the blackness of space. Add blue and purple at the bottom, where the curtain touches the distant northern mountains. Watch as the colours shift and flow, responding to invisible changes in the solar wind, creating patterns that never repeat exactly, that exist for a moment and then transform into something new. Let these colours fill your mind, replacing whatever thoughts or worries you carried into this time of the rest. There's nothing you need to do, nowhere you need to be. The aurora dances whether you're awake or asleep, whether you're watching or not, and there's a profound peace in that constancy, in knowing that some things continue regardless of our participation or attention. The colours of the aurora are also affected by the viewing conditions on the ground. Light pollution from cities washes out the fainter colours, leaving only the brightest greens visible. This is why the best aurora viewing happens in remote locations, far from human lights, where the darkness is complete and even the subtlest colours can shine through. On a truly dark night, under a strong aurora, you can see gradations of colour that seem impossible. The way green transitions to yellow and then to red, the way purple edges blend into blue, the way the entire display pulses and breathes like a living thing. It's a privilege to witness such purity of colour, such unfiltered beauty, and those who have seen it often describe it as a life-changing experience, a moment when they felt truly connected to something larger than themselves. Let's drift deeper now into understanding the invisible architecture that makes the aurora possible, Earth's magnetic field, that silent guardian that has protected our planet for billions of years. This magnetic field isn't something we can see or feel directly in our daily lives, yet it's constantly there, extending from deep within Earth's core out into the vacuum of space, shaping the very environment that allows the aurora to exist. As you rest here, the magnetic field is passing through your body, through the walls around you, through everything, completely unnoticed yet fundamentally important to life as we know it. The source of Earth's magnetic field lies nearly 3,000 kilometers beneath our feet in the planet's outer core. Here, liquid iron and nickel flow in vast currents, driven by the heat escaping from Earth's even deeper inner core and by the planet's rotation. This motion of conductive liquid metal generates electric currents, and these currents in turn create magnetic fields in a self-sustaining process scientists call the geodynamo. It's similar in principle to how an electric generator works, converting mechanical motion into electromagnetic energy, except that Earth's generator has been running continuously for over 3 billion years, requiring no maintenance, no external power source, just the heat left over from the planet's formation and the slow decay of radioactive elements deep within the Earth. The magnetic field that emerges from this process is roughly shaped like a bar magnet, tilted slightly relative to Earth's rotation axis. The magnetic field lines exit Earth near the South Pole, arc through space, and re-enter near the North Pole. But it's important to note that Earth's magnetic poles don't align exactly with the geographic poles. There's an offset of about 11 degrees, which means that magnetic north, the direction a compass points, is not the same as true north. This misalignment has consequences for where auroras appear, since auroras follow the magnetic field lines, not the geographic coordinates. The auroral oval, that ring of frequent aurora activity, is centered on the magnetic poles, not the geographic ones, which is why auroras can sometimes be seen from places you might not expect, based on latitude alone. What's particularly fascinating and rather soothing in its own way is that Earth's magnetic field is not constant over long timescales. It wanders, it weakens and strengthens, and every few 100,000 years or so it completely flips, with magnetic north becoming magnetic south, and vice versa. We know this from studying ancient rocks that contain magnetic minerals. These minerals align themselves with Earth's magnetic field as the rocks formed, essentially freezing a record of the field's direction at that moment in time. By studying rocks of different ages, scientists have discovered that these reversals happen irregularly, sometimes with millions of years between them, sometimes with only tens of thousands. We're currently in a period of relatively stable magnetic field orientation, but the field is weakening, leading some scientists to wonder if we might be approaching another reversal. Don't worry though. Even if a reversal happens, it takes thousands of years to complete, and life has survived many such reversals in the past. The aurora would continue to dance throughout the transition, perhaps appearing at unusual latitudes, perhaps putting on even more spectacular shows as the field reorganizes itself. The magnetosphere, that region of space dominated by Earth's magnetic field, is not spherical despite its name. On the side facing the Sun, the solar wind compresses it to about 60,000 kilometers above Earth's surface. Still a vast distance, but small compared to the extent of the field on the night side, where it stretches out into a tail millions of kilometers long. This magnetotail extends far beyond the Moon's orbit, creating a wake in the solar wind much like a boat creates a wake in water, and it's in this magnetotail that some of the most interesting processes occur. When the solar wind is particularly strong, or when the interplanetary magnetic field carried by the solar wind has the right orientation, energy can be stored in the stretched magnetic field lines of the magnetotail, like energy stored in a stretched rubber band. Eventually, this energy is released in what's called a magnetospheric substorm, and the field lines snap back toward Earth, accelerating particles down into the atmosphere and creating sudden intensifications of the aurora. These substorms are a major reason why the aurora is dynamic, why it doesn't just glow steadily, but pulses and surges and sometimes explodes across the sky in dramatic displays. The magnetic field lines themselves can be thought of as invisible highways along which charged particles travel. Near the equator, the field lines are nearly horizontal, running parallel to Earth's surface at high altitudes, which is why auroras don't typically occur at low latitudes. The particles have no reason to dive down into the atmosphere there. But near the poles, the field lines are nearly vertical, plunging down toward Earth's surface, and this is where the particles follow them downward, guided like beads on a string, until they reach the altitudes where the atmosphere is dense enough for collisions to occur. The particles spiral along these field lines, their paths dictated by the electromagnetic forces acting on them, creating the vertical structures we sometimes see in the aurora, those rays and curtains that seem to hang from the sky like luminous drapes. There's a region called the auroral oval, a ring-shaped zone centered on each magnetic pole, where auroras occur most frequently. This oval expands during strong geomagnetic storms and contracts during quiet periods, but it's always there, always active to some degree. If you could watch Earth from space over a period of hours or days, you'd see this oval pulsing and breathing, bright during active times, dimmer during quiet times, but never completely dark. It's like a crown of light that Earth wears constantly, invisible to most of the planet's inhabitants, but always present for those living at high latitudes or for astronauts looking down from above. The International Space Station sometimes passes beneath the aurora, and astronauts have described the experience as surreal, looking up at this phenomenon that people on the ground look up at, seeing it from below, watching the curtains ripple and flow beneath them like inverted waterfalls of light. The strength of the magnetic field at Earth's surface varies from place to place. It's strongest near the magnetic poles and weakest near the magnetic equator. This variation affects not just where auroras appear, but also how cosmic radiation reaches the surface. The magnetic field deflects most charged particles from space, protecting us from radiation that would otherwise be harmful to life. The auroral ovals represent the weak points in this shield, where particles can more easily reach the atmosphere, but even there they're absorbed by the air long before they reach the ground. Commercial airline pilots flying polar routes do receive slightly higher radiation doses than they would at lower latitudes, simply because they're closer to where particles are entering the atmosphere, but the amount is still small, well within safety limits for even frequent flyers. One of the beautiful aspects of the magnetic field is its self-healing nature. When the solar wind pushes on it, compressing it, the field responds by storing energy and then gradually relaxing back to its normal shape once the solar pressure decreases. When a burst of solar particles arrives, the field guides them toward the poles, away from the more vulnerable equatorial regions. When magnetic field lines are stretched and twisted by solar wind interactions, they eventually reconnect and relax, releasing the stored energy in the process but returning to a more stable configuration afterward. It's a dynamic equilibrium, constantly adjusting and responding but always maintaining its overall structure and function. There's something almost alive about it, the way it adapts and reacts, even though it's entirely a physical process with no consciousness or intent behind it. Scientists study the magnetic field using satellites, ground-based magnetometers, and even measurements of magnetic minerals in archaeological artifacts. The European Space Agency's Swarm mission, for example, consists of 3 satellites that measure Earth's magnetic field with unprecedented precision, tracking its changes over time, mapping its variations across the globe. This data helps us understand not just the current state of the field, but how it's evolving, how the dynamics of the core are changing, how external influences like the solar wind affect it. It's a field of study that connects the deepest parts of our planet with the farthest reaches of space, showing how everything is interconnected, how what happens in Earth's core affects what happens in near-Earth space, which affects what happens in the upper atmosphere, which produces the aurora that inspires wonder in anyone who sees it. The magnetic field also interacts with the fields of other planets in our solar system. Mars, as I mentioned earlier, lost its global magnetic field billions of years ago, and without that protection, its atmosphere was gradually stripped away by the solar wind. Venus has no intrinsic magnetic field either, though it does have an induced magnetosphere created by the interaction of the solar wind with its thick atmosphere. Jupiter and Saturn have powerful magnetic fields, much stronger than Earth's, and they too have auroras, though these are powered not just by the solar wind but also by particles from their moons and rings. Observing auroras on other planets helps us understand our own better, showing us what's universal about these phenomena and what's unique to Earth. As you rest here, you're resting in the embrace of this magnetic field, this invisible protector that has made life on Earth possible. Every breath you take is made possible by the atmosphere that the magnetic field has helped preserve. Every moment of consciousness you experience is possible because harmful radiation has been deflected away. And the aurora, that beautiful light show, is a visible manifestation of this protection, a reminder that we're safe here on this small planet, shielded from the harshest aspects of space by forces we can barely perceive, but which work tirelessly, constantly, to maintain the conditions necessary for life. Let that thought settle over you like a warm blanket as your body relaxes deeper, as sleep begins to approach with gentle steps. The auroral ovals aren't actually centered on the magnetic poles themselves, but on slightly offset points called the magnetic dip poles, where Earth's magnetic field is perfectly vertical. There are 2 such points, one in each hemisphere, and they move over time as the magnetic field shifts and changes. Currently, the northern magnetic dip pole is located in the Canadian Arctic, north of Hudson Bay, but it's been moving northward at an accelerating rate, travelling about 40 kilometers per year lately. This movement is due to changes in the flow of molten iron in Earth's outer core, chaotic convective currents that are impossible to predict with precision. The aurora follows this movement, meaning that the best viewing locations slowly change over decades and centuries. Places that once rarely saw auroras might see them more frequently in the future, while traditional aurora viewing locations might see them less often. It's a reminder that even things as fundamental as Earth's magnetic field are in constant flux. Nothing is truly permanent, everything flows and changes, much like the thoughts in our minds as we drift towards sleep. The magnetic field lines near the poles don't just guide particles down into the atmosphere, they also channel them back out. Particles can bounce between the northern and southern hemispheres along field lines, spending minutes or even hours spiraling back and forth before finally colliding with an atmospheric molecule. This means that auroras in the north and south are not completely independent phenomena, They're connected by these shared magnetic field lines, by particles that travel from one hemisphere to the other. During strong geomagnetic storms, auroras in both hemispheres brighten simultaneously, driven by the same influx of solar particles, creating mirror images of light in the Arctic and Antarctic skies. It's a beautiful symmetry, a reminder that Earth's magnetic field unites the planet, connecting pole to pole through invisible lines of force that arch through space high above the equator. Now, my friend, as you rest in this peaceful state, let's explore how the aurora has touched human consciousness throughout history, how it has inspired stories and art, how it has been interpreted and reinterpreted by different cultures across time. The aurora is not just a physical phenomenon, it's also a cultural one, a source of meaning and wonder that transcends the scientific understanding of what causes it. Even now, when we know about solar wind and magnetic fields and atmospheric chemistry, the aurora still inspires awe, still makes us feel small and connected to something greater than ourselves. For the indigenous peoples of the Arctic, the Sami in northern Scandinavia, the Inuit in Canada and Greenland, the various tribes of Alaska and Siberia, the aurora has been a constant presence in their lives for thousands of years. These are people who live in darkness for months at a time during the polar winter, when the sun doesn't rise above the horizon for weeks or months on end. In that darkness, the aurora becomes one of the few sources of light besides the moon and stars, and it's no wonder that it took on deep spiritual significance. Many Arctic cultures saw the aurora as spirits of the dead, dancing in the sky. The Sami called them the lights of the dead, and believed that you should be quiet and respectful when the aurora appeared, avoiding loud noises or whistling, which might attract the spirit's attention. Some believed that the lights could snatch up anyone who was careless or disrespectful. Other interpretations were more playful. Some Inuit groups believed that the aurora was caused by spirits playing ball with a walrus skull, kicking it across the sky. Others saw the lights as torches carried by spirits to guide souls to the afterlife. In Norse mythology, the aurora was connected to the Bifrost, the rainbow bridge between Midgard, the world of humans, and Asgard, the realm of the gods. Some Norse legends describe the aurora as reflections from the shields of the Valkyries, those warrior maidens who chose which soldiers would die in battle and escorted their souls to Valhalla. There's something beautiful about how different cultures, separated by vast distances and having no contact with each other, all looked at the same phenomenon and created stories to explain it. Stories that reflected their values, their fears, their hopes. In medieval Europe, where auroras are less common than in the far north but still occasionally visible, bright auroral displays were sometimes interpreted as omens. A particularly vivid red aurora might be seen as blood in the sky, a warning of impending war or disaster. Historical records mention auroras appearing before major battles or during times of plague and famine, though this was likely confirmation bias. People remembering the auroras that coincided with bad events and forgetting the many auroras that preceded peaceful times. Still, the fact that auroras were recorded at all in medieval chronicles shows how significant they were, how they stood out as unusual and noteworthy events worth documenting for future generations. The first scientific investigations of the aurora began in the 17th and 18th centuries, as European scientists started to approach natural phenomena with systematic observation and experimentation rather than relying solely on folklore and tradition. The Italian astronomer Galileo Galilei is credited with coining the term aurora borealis in 1619. combining the name of Aurora, the Roman goddess of dawn, with Boreas, the Greek god of the north wind. It was a poetic name for a phenomenon that Galileo himself didn't fully understand. He believed the auroras were sunlight reflecting from the atmosphere, a reasonable hypothesis given the limited knowledge of his time, but ultimately incorrect. It would be another 2.5 centuries before the true cause of auroras was understood. In the 19th century, as scientists began to understand electricity and magnetism, the connection between auroras and Earth's magnetic field started to become clear. The Norwegian scientist Christian Birkeland conducted groundbreaking experiments in the early 1900s, creating miniature auroras in his laboratory by firing electrons at a magnetized sphere in a vacuum chamber. He correctly theorized that the aurora was caused by charged particles from the sun interacting with Earth's magnetic field, though his ideas were not immediately accepted by the scientific community. It took decades of further research, including observations from rockets and satellites in the space age, before Birkeland's theories were confirmed and expanded into the modern understanding we have today. The aurora has inspired countless artists over the centuries. Painters have attempted to capture its ethereal beauty on canvas, though many have noted the difficulty of representing something so dynamic and three-dimensional in a static, two-dimensional medium. The challenge isn't just technical, but also emotional. How do you convey not just what the aurora looks like, but how it makes you feel? Some artists have taken realistic approaches, carefully documenting the colours and shapes they observed. Others have been more impressionistic, using the aurora as a starting point for explorations of light and colour that go beyond literal representation. The Norwegian painter Harald Zolberg's Winter Night in the Mountains from 1914 includes a subtle aurora in the background, adding to the painting's sense of quiet, cold beauty. The aurora has also appeared in indigenous art from Arctic cultures, woven into traditional clothing patterns, carved into artifacts, incorporated into stories told through visual means. In literature, the aurora has served as both setting and symbol. Jules Verne sent his characters into the far north in search of adventure, and the aurora appears in several of his novels as a marker of the exotic remote places his protagonists explore. Philip Pullman's His Dark Materials trilogy features the aurora prominently, making it a gateway to other worlds, a thin place where the boundaries between realities become permeable. This symbolic use of the aurora as a threshold, a boundary, a point of transition, appears in many stories and reflects perhaps a deep intuition about what the aurora represents, a meeting point between Earth and space, between the solid and the ethereal, between what we can touch and what we can only observe. The aurora even plays a role in modern popular culture. It appears in films and television shows set in northern regions, often used to establish atmosphere or to mark significant moments. It's featured in countless photographs shared on social media, images that go viral because of the aurora's undeniable visual impact. There are even aurora tourism industries now in places like Iceland, northern Norway, Alaska, and Canada's Yukon Territory, where people travel specifically to see the northern lights, staying in special aurora viewing lodges, taking guided tours to dark sky locations, waiting patiently in the cold for the sky to light up. It's one of the few astronomical phenomena that people will go to great lengths and expense to witness, recognizing that seeing the aurora in person is an experience that can't be fully replicated by photographs or videos, no matter how high the quality. Some people claim to have heard the aurora, describing it as a crackling or hissing sound, soft but distinctly audible during particularly strong displays. For a long time, scientists were skeptical of these reports, since the aurora occurs at such high altitudes that sound waves produced there shouldn't be able to reach the ground. They would be absorbed or scattered in the tenuous upper atmosphere long before they could propagate to where people could hear them. However, recent research has suggested that what people hear might be real, just not directly from the aurora itself. The theory is that strong auroras create electrical charges on nearby surfaces, the ground, buildings, trees, and the sparking or discharge of these charges might produce the sounds that observers report. It's still an area of active research, but the possibility that the aurora has a sonic as well as a visual component adds another layer to its mystery and appeal. The aurora has also been associated with various health effects and psychological experiences over the years. Some people report feeling energized or emotionally moved by viewing auroras, while others describe a sense of peace or connection to nature. There's no solid scientific evidence that the aurora directly affects human physiology. We're well shielded from the charged particles that cause it, but the psychological impact of witnessing such a spectacular natural phenomenon is undeniable. It's an experience that tends to stay with people, that they remember vividly even years later, often describing it as one of the most beautiful things they've ever seen. There's something about the combination of factors, the darkness, the cold, the silence of a winter night, and then this explosion of colour and movement in the sky, that creates a profound experience, one that seems to bypass rational analysis and speak directly to something deeper in us. The aurora has been photographed extensively, especially in the modern era with digital cameras that can capture long exposures and bring out colours invisible to the naked eye. These photographs have done much to popularise the aurora, making it accessible to people who might never travel to see it in person. But photographers who specialise in aurora photography will tell you that images, no matter how stunning, can't fully capture the experience. The aurora isn't just a static image, but a constantly changing display, flickering and flowing, expanding and contracting, brightening and fading. It has a presence, a sense of dimensionality and movement that still images can't convey. Time-lapse videos come closer, showing how the aurora evolves over minutes and hours, but even these are compressed, edited versions of reality. To truly experience the aurora, you need to be there, in the cold and dark, watching it with your own eyes, feeling yourself as part of the scene rather than an outside observer. Astronauts have a unique perspective on the aurora, viewing it from above rather than below. From the International Space Station, the aurora appears as glowing curtains far below, draping over Earth's polar regions. Astronauts have described seeing the green glow outlining the curve of the planet, a delicate ribbon of light marking the boundary between the solid Earth and the blackness of space. Some have even seen red auroras extending high enough that they were at the same altitude as the space station, looking out at them horizontally rather than down at them. These observations from space have been invaluable for scientific research, providing a perspective that can't be obtained from ground-based observations and revealing structures and behaviours in the aurora that would otherwise remain hidden. In recent years, citizen scientists have become involved in aurora research through projects that collect reports of aurora sightings from around the world. These reports help scientists track the extent of auroral displays during geomagnetic storms and provide data on when and where auroras are visible. Some projects also encourage people to submit photographs, which can be analysed for information about aurora colours, structures and movements. This democratization of aurora science allows anyone with an internet connection to contribute to our understanding of these phenomena, connecting professional researchers with a global network of observers who share a passion for the aurora. The aurora has even influenced the naming of things far removed from atmospheric physics. The aurora butterfly, for instance, is a species found in Australia named for its shimmering iridescent wings that evoke the colours of the northern lights. Several ships have been named Aurora over the centuries, including vessels used for polar exploration. The element selenium was named after Selene, the Greek goddess of the moon, continuing the tradition of naming elements after celestial phenomena that started with cerium, Ceres, uranium, Uranus, and others. These naming choices reflect how deeply the aurora and other celestial phenomena have penetrated human consciousness, becoming reference points not just for scientists but for anyone seeking to evoke beauty, mystery, or the natural world. There's a certain comfort in knowing that the aurora has been witnessed by countless humans throughout history, that people thousands of years ago looked up at the same lights we can see today, probably feeling the same mix of wonder and insignificance in the face of such beauty. The aurora connects us across time, a shared experience that transcends culture, language, and era. Whether you're an Inuit hunter in the Canadian Arctic 1,000 years ago, a Viking warrior sailing the North Atlantic, a 19th century scientist making careful observations with primitive instruments, or a modern tourist with a camera and a hotel reservation, the aurora treats you all the same. It dances above, indifferent to who's watching, beautiful simply for the sake of being beautiful. Let's talk about some of the more unusual aurora phenomena that have been observed and documented. Sometimes, during particularly strong geomagnetic storms, the aurora can be seen at unusually low latitudes, far from its typical polar habitats. There are historical records of auroras being seen from the Caribbean, from southern Europe, from Japan, from Australia. Places where the aurora is normally never visible. These extreme events are associated with powerful solar storms, times when the sun releases massive amounts of energy that compress Earth's magnetosphere and expand the auroral oval far beyond its normal extent. The most famous such event in modern times was the Carrington event of 1859, named after the British astronomer Richard Carrington, who observed the solar flare that caused it. The resulting geomagnetic storm was so powerful that auroras were seen as far south as the Caribbean and Hawaii, and telegraph systems were disrupted worldwide, with some telegraph operators reporting that they could continue sending messages even with their batteries disconnected, powered solely by the electrical currents induced in the telegraph lines by the geomagnetic storm. If an event like the Carrington event happened today, it would likely cause significant disruption to our technology-dependent civilization. Satellites could be damaged or destroyed, power grids could fail, GPS systems could be disrupted, communications networks could be affected. This is why scientists monitor the sun constantly now, watching for signs of large solar flares and coronal mass ejections, trying to provide advance warning of incoming geomagnetic storms so that vulnerable systems can be protected. It's a reminder that while the aurora is beautiful, the solar activity that causes it can also have practical consequences for modern life. Though for you, resting here in this moment, these concerns are distant and abstract, just interesting thoughts to drift past as you sink deeper into relaxation. There are also rare auroral phenomena that even experienced aurora watchers don't often see. One is called STEVE, an acronym for Strong Thermal Emission Velocity Enhancement. STEVE appears as a narrow ribbon of purplish light often accompanied by green vertical structures called picket fence aurora. It was only recently recognized as distinct from normal auroras, thanks largely to observations by amateur aurora photographers who noticed that these features didn't behave like typical aurora and brought them to the attention of scientists. Research is still ongoing to fully understand Steve, but it appears to be caused by different mechanisms than normal aurora, involving flows of hot plasma in the ionosphere rather than precipitation of energetic particles. It's a reminder that even phenomena as well studied as the aurora can still surprise us, still reveal new aspects that we didn't know existed. Another unusual aurora phenomenon is the pulsating aurora, which appears as patches of light that brighten and dim rhythmically, like a slow-motion strobe light. These pulsations occur with periods of a few seconds to tens of seconds, and are thought to be caused by waves in the Earth's radiation belts that periodically dump particles into the atmosphere. Pulsating auroras are most common in the morning hours after midnight and can last for hours, creating a hypnotic display of light that flickers on and off like the breathing of some vast celestial being. Watching a pulsating aurora is an almost meditative experience, the regular rhythm of the brightening and fading creating a natural pulse that you can synchronize your own breathing with, enhancing the sense of connection with the phenomenon you're observing. There are also subvisual auroras, displays that are too faint to see with the naked eye, but can be detected by sensitive instruments or long-exposure photography. These occur frequently, even during geomagnetically quiet times, representing a baseline level of solar particle precipitation that's always happening at the poles. You could be standing outside on a clear night in Alaska or northern Canada, seeing no aurora at all, yet if you set up a camera for a long exposure, you might capture faint green glows or arcs that your eyes couldn't perceive. This invisible aurora is a reminder that the interaction between the solar wind and Earth's magnetosphere never stops, that even when we can't see the aurora, the processes that create it are still ongoing, quietly, persistently, like the beating of a heart. The aurora also has a southern counterpart, the aurora australis or southern lights, which occurs in the Antarctic region. The southern lights are essentially identical to the northern lights in terms of their physics, caused by the same processes, displaying the same colours and structures, but they occur over one of the most remote and inhospitable regions on Earth. Very few people get to see the southern lights directly, since there are few inhabited places at the necessary latitudes in the southern hemisphere. The southern tip of South America, New Zealand's South Island and Tasmania occasionally see auroras during strong geomagnetic storms, but these sightings are much rarer than northern light sightings at equivalent northern latitudes, simply because there's so much less land at high southern latitudes. The aurora australis is mostly witnessed by scientists at Antarctic research stations, by sailors crossing the Southern Ocean, and by astronauts looking down from space. It's the same phenomenon as the aurora borealis, yet it feels more mysterious, more remote, occurring over the ice and penguins rather than over human communities. The aurora has been used in practical ways beyond tourism and science. During World War II, military forces sometimes used the aurora as a navigational aid, since its position gave them a rough indication of direction, even when other navigation methods were unavailable. Pilots flying in polar regions learned to recognize the aurora and use it to maintain their bearings. The aurora's light has also been used by photographers working in the Arctic, providing enough illumination during the dark winter months to capture images without artificial lights. Of course, this only works during active auroral displays, but in the heart of the auroral zone, during winter, that can be fairly often, giving photographers a natural studio light that's far more interesting than anything they could create artificially. In indigenous Arctic cultures, the aurora was not just observed but incorporated into daily life and seasonal rhythms. The appearance of certain auroral forms might signal good or bad luck for hunting. The colours of the aurora might be interpreted as messages from ancestors. Stories about the aurora were told to children as both entertainment and education, teaching them about their culture's cosmology and their place in the natural world. These stories have been passed down through generations, sometimes surviving even as other aspects of traditional culture have been lost or changed through contact with outside societies. Today, there's a growing effort in many Arctic communities to preserve and revitalize traditional knowledge about the aurora, recognizing it as an important part of cultural heritage that connects people to their ancestors and to the land. The aurora has also influenced the development of scientific instruments and techniques. The need to measure and understand auroras drove the invention of various types of cameras, spectrometers, and magnetometers designed to operate in the harsh Arctic environment. The analysis of auroral data has contributed to developments in data processing, imaging techniques, and computer modelling that have found applications far beyond aurora research. The study of how charged particles interact with gases in Earth's atmosphere has informed our understanding of similar processes in other contexts, from neon signs to nuclear fusion research. Science is cumulative, each field building on insights from others, and auroral science has both drawn from and contributed to this larger edifice of human knowledge. As you rest here, perhaps you're beginning to feel sleep approaching, that gentle pull toward unconsciousness that's so pleasant when you don't resist it. The aurora continues its dance whether we're awake to see it or not, and there's something comforting about that constancy. It's been happening for billions of years since Earth first developed a magnetic field and an atmosphere, long before humans existed to witness it. It will continue for billions more years, until the sun expands into a red giant and consumes the inner planets, including Earth. In the grand sweep of cosmic time, the aurora is eternal, and we're the briefest of visitors, lucky enough to exist during a moment when we can appreciate it. But that's okay. Brief moments can be profound. A single viewing of the aurora can stay with someone for their entire life, can change their perspective, can remind them that there's more to existence than the daily grind of mundane concerns. The aurora represents in many ways the boundary between Earth and space, between the familiar and the cosmic. It occurs in the thermosphere, that region of the atmosphere that's already more space than air, where satellites orbit and where the atmosphere is so thin that molecules rarely collide. Yet it's still part of Earth's system, still connected to the solid planet, below through the magnetic field lines that channel the particles that create it. The aurora is neither fully of Earth nor fully of space, but exists in between, a hybrid phenomenon that requires both the planet and the cosmos to exist. It's a physical manifestation of how interconnected everything is, how nothing exists in isolation, how the sun's activity affects Earth, how Earth's interior affects its magnetic field, how that magnetic field affects the solar wind, how the resulting processes create beauty that affects human consciousness and culture. Everything is connected, everything flows into everything else, and the aurora is one visible thread in that vast web of relationships. If you were to ask someone who has seen the aurora what it means to them, you'd get many different answers. Some would talk about the beauty, the colours, the movement. Others would mention the feeling of being small in the face of nature's grandeur. Still others might discuss the spiritual or emotional impact. the sense of connection to something larger than themselves. Some would focus on the scientific understanding, finding beauty in the explanation of how and why the aurora occurs. None of these perspectives is wrong. The aurora is all of these things and more, and each person brings their own background and expectations to the experience, finding in it whatever they're prepared to find. This multiplicity of meaning is part of what makes the aurora so universally appealing. It offers something to everyone, regardless of their interests or worldview. Let's consider the aurora's role in climate and atmospheric science. While the aurora itself doesn't significantly affect climate, the energy deposited by auroral particles is tiny compared to the energy the lower atmosphere receives from the sun. Studying the aurora has helped scientists understand how energy flows through Earth's atmosphere. The processes that create auroras also create ionospheric currents that can affect radio communication and navigation systems. During strong geomagnetic storms, these effects can be significant, disrupting GPS signals, interfering with radio communications, even inducing currents in power lines that can damage transformers. Understanding the aurora and the space weather that causes it has practical applications for protecting technological infrastructure, making auroral science not just a pursuit of pure knowledge, but also a matter of practical importance. The thermosphere, where most auroral light is emitted, is a region of the atmosphere that's difficult to study. It's too high for balloons or aircraft, but too low for satellites to orbit, without eventually being dragged back to Earth by atmospheric friction. Rockets can briefly pass through this region, and they've been used to make in situ measurements of auroral processes, but they provide only brief snapshots. The aurora itself provides a way to remotely sense conditions in the thermosphere by observing the aurora's colors, brightness, and motion. Scientists can infer information about atmospheric composition, temperature, and dynamics at altitudes that are otherwise hard to study. In this way, the aurora serves as a natural laboratory, a place where we can observe fundamental plasma and atmospheric processes that are difficult or impossible to replicate in human-made laboratories on the ground. There's a concept in aurora science called auroral electrojet, which refers to intense electrical currents that flow in the ionosphere during auroral activity. These currents can be thousands of kilometers long and carry millions of amperes of current, making them some of the largest electrical currents on Earth. They're one reason why strong geomagnetic storms can affect power grids. The changing magnetic fields associated with these currents induce voltages in long conductors like power lines, and if these induced voltages are large enough, they can damage electrical equipment. The auroral electrojet is yet another reminder that the aurora, for all its beauty, is part of a larger system that includes powerful electrical and magnetic phenomena, forces that we rarely notice in daily life, but that are always present, always active. The study of auroras has also contributed to our understanding of planetary atmospheres throughout the solar system. Every planet with a magnetic field and an atmosphere has auroras, though they're produced by different mechanisms depending on the planet's specific conditions. Jupiter's auroras, for example, are powered not just by the solar wind but also by material ejected from its moon Io, which has active volcanoes that constantly pump sulfur and oxygen into Jupiter's magnetosphere. Saturn's auroras have been observed by the Hubble Space Telescope and by spacecraft like Cassini, revealing beautiful displays that are similar to but distinct from Earth's auroras. Even planets without global magnetic fields like Mars and Venus, have localized auroral phenomena in regions where the solar wind interacts directly with the atmosphere or with localized crustal magnetic fields. By studying these diverse auroral phenomena, we gain insights into how magnetic fields, atmospheres, and solar or stellar winds interact. Knowledge that's relevant not just for understanding our own solar system, but also for thinking about exoplanets around other stars. As we drift toward the end of our journey together tonight, let's return to a personal, intimate scale. Imagine yourself standing in the Arctic darkness, your breath forming clouds in the cold air, your feet crunching on frozen snow. Above you, the aurora begins to dance, first a faint glow on the northern horizon, then brightening, expanding, flowing overhead like a river of light. You watch as curtains as green ripple and wave, as touches of red appear at the top, as the whole display pulses and breathes with a rhythm that seems almost alive. You feel the cold on your face, see the stars bright and steady beyond the moving aurora, hear the absolute silence of the winter night broken only by your own breathing. And in that moment, you feel connected to this place, to this phenomenon, to the cosmos itself. You're witnessing something that has been happening for eons, something that will continue long after you're gone, and there's both humility and joy in that realization. The aurora doesn't care if you're watching, it doesn't care if you understand it or appreciate it or even if you exist at all. It simply is a consequence of physical laws and processes that have no awareness or intention. Yet somehow, that doesn't diminish its impact. If anything, it enhances it. The aurora's indifference to us makes our appreciation of it all the more precious, all the more meaningful. We choose to find beauty in it, to create stories about it, to travel great distances to see it, to study it scientifically, to photograph it, to share it with others. The meaning isn't in the aurora itself, but in how we respond to it, in what it evokes in us. And what it evokes, more often than not, is a sense of wonder, a feeling of being part of something larger, a reminder that the universe is full of beauty if we just take the time to look for it. Tonight, as you drift off to sleep, you carry with you the knowledge of the aurora, how it's formed, what creates its colours, how Earth's magnetic field guides it, how it has inspired humans throughout history. But more than the facts, you carry the feeling, the sense of the aurora as something peaceful and eternal, a dance of light that continues whether we're watching or not. Let that image fill your mind as you fall asleep. Curtains of green and red and purple flowing across a star-filled sky, silent and beautiful, a gift from the sun to the earth, from the cosmos to anyone who takes the time to look up and appreciate it. The solar wind continues to flow, Earth's magnetic field continues to guide. The atoms in the thermosphere continue to be excited and to release their energy as light. And somewhere, right now, the aurora is dancing above the polar regions, visible to the fortunate few who happen to be in the right place at the right time, invisible to the rest of us, but no less real, no less beautiful. It's always there, this cosmic lullaby, this gentle reminder that we live in a dynamic, interconnected universe full of wonders that we're only beginning to understand. May the peace of the aurora be with you as you sleep. May its gentle light guide your dreams. May you wake refreshed, carrying with you a little of the wonder we've explored together tonight. The aurora will be there tomorrow night and the night after, and for countless nights to come, waiting patiently for those who wish to witness its eternal dance. Sleep well, my friend, until we meet again on another journey of discovery and rest. Good night.